So I thought we'll take pictures in the end.
Olivier sent me an email.
All right, so this is the IRTF open meeting in Seoul. Can I ask you guys that you keep the doors closed because the noise is really distracting? Matt? Yeah, bar the doors. All right, this is the IRTF IPR policy. It's basically the same one as the IETF IPR policy, meaning if you make a contribution, you are required to disclose any IPR that you hold or that a organization that you work for holds, that you have personal knowledge of, and we request that you file other IPR and contributions that you know about. So you should know all this. If you don't, you should really read it. The slides are uploaded. My slides were very late, so I apologize for that, but they're up now. You can dial in remotely. You probably figured this out already. We have two mailing lists. One is an announced list that sees very little traffic, basically when new RFCs get published and new groups start and stop. There's a discussion list that sees also very few traffic because nothing much gets discussed that is IRTF wide. Most of it is on the individual research group lists. Today we have the usual like 5 to 10 minutes of me telling you what has happened in the last couple of months, followed by the two main events, which are the Applied Networking Research Prizes. These are the last two prizes for 2016. We had 6 in total because we had a pretty large number of submissions. And the 2017 selection is actually going on at the moment. Maybe I'll say a little bit more about this later. So where are we? We have 10 research groups meeting, which is a lot. We have 11 chartered right now, so almost all of them are meeting except for Gaia, including a new one, which is MapRG, Measurement Analysis for Protocols. And we have a proposed network machine learning working group meeting. That'll be their last meeting as a proposed group. And after this, me and Allison, who's going to succeed me, will sit down and decide whether we want to charter them formally or whether they have run out of runway. You are in the IRTF open meeting on Thursday morning. The IAB reviews one of the research groups traditionally during each meeting. This time it's the Human Rights Protocol Considerations group, which had a meeting earlier today, which was very interesting, I hear. I wasn't there. Bit more on MapRG since it's a new group, right? So this is, you can think of this if you've been around long enough, this is the second iteration of the IMRG, the Internet Measurement Research Group. So the idea is that there's a lot of measurement efforts going on in academia, but also outside, but the results are not really widely used to drive engineering, and the idea is to bridge that gap. So there's a lot of things that are in scope here that are listed in these bullets. They're going to have a meeting later on. The last few meetings that they had as a proposed group are very interesting, so I have sort of high hopes that they keep up the history of interesting presentations that they've managed to invite. We have a new addition to these slides that I'm going to do from now on until I step down in March, which is called Research Group News. So far we have one news item, unless there's something in my inbox that I missed. The HRPC that I just mentioned, Human Rights Protocol Considerations, they have their first draft going into last call next week. It'll be a long last call, and they ask for wide reviews, and it's an interesting document because it's not very technical, but it is interesting in that it makes observations about how protocol design can impact fundamental human rights. It is broadly applicable to basically everything we do in the IRTF and IETF. So if you have nothing better to do on the flight home, it's a good read. And send Niels and the guys feedback. We have an IRTF RFC stream. It is not quite as busy as the IETF stream, but we did manage to publish 4 RFCs since the last meeting, 3 of which came from the Information-Centric Networking Research Group, and 1 came from Gaia, their first document. And there are a few more in the queue from various other research groups. So probably going to see a few more by Chicago. These are the 4 that were published. research challenges in ICN, video streaming over ICN, security considerations for ICN. And then Gaia has a taxonomy document on alternative network deployments, which is actually an interesting read. Last time I said that the IAB wanted feedback on the candidates for IRTF chair starting March 2017. You've sent feedback. That was very helpful to the IAB in making a decision. The selection was Alison Menken, who is not really a newbie, but will take up this role. There's a little bio there that those of you in the first row can probably even read. Very happy with the selection. Thank you for volunteering, and I hope you have a good time. I had a good time. She's sitting up there if you want to meet her later on. All right. We have two things that start with applied networking research. One is a workshop and one is a prize. This is about the workshop. So the URL is wrong because I copied this from Berlin. So it should be 2017 there. So we're doing this again. We did the first one in Prague. We're doing one in 2017. So this is an academic peer-reviewed workshop. It's technically co-sponsored by ACM Sitcom. We have two TPC chairs for next year, which are Renata Teixeira and Jörg Ott. They're both on the Sitcom Executive Committee, which tells you a little bit that Sitcom actually takes this as important. Proceedings are open access, and the plan is, or we will co-locate this with IETF in Prague. It will be on the Saturday before the IETF meeting in Prague. It's a full-day event. The call for papers should be out soon, probably still this year. I'm guessing the submission deadline will be somewhere in the February timeframe, maybe March. Peer review takes a month, so notifications probably April, May. It's an interesting event. So if you, even if you don't send anything in, you should maybe think about attending it. You can look on the webpage for the 2016 meeting to see what the papers and presentations were. It was a pretty successful event. So if you are in Prague on Saturday because you want to arrive early to get rid of the jet lag before the craziness starts, come to this. The second thing that starts with applied networking research is the prize. We've been doing this for 5 years now, so this should not be new anymore. It's together with ISOC. We had 53 nominations for 2016, which is the largest ever. For 2017, the nomination period just ended, and I think we have 40, but one was a double nomination. So we have 39 that entered the selection. The number is slightly lower, but I think the quality, based on what I've seen, glancing through the submissions, is easily as high as it was this year. So I'm expecting we're going to have, again, a very tough decision to pick a few of these for the prize. Selection committee is some IETFers, some IRTFers, and by now we've also added a few of the usually senior professors from the awarded papers over the last few years, and I think we're going to keep doing that. So that we actually have academic representation on the committee, specifically from those sort of people that seem to have successfully done interesting research in the past, so they can help us pick the next crop. And part of the award is the talks that are going to follow this. And I should say Comcast is again extended to sponsor this for I don't know how many years we're committed, but at least 1 year. So thank you very much. If other organizations would like to support the ANRP, Matt Ford from ISOC will be super thrilled to talk to you. You might even buy you a beer or something. But all kidding aside, right? So this helps us because there is a cost associated with this, because it's a travel grant to come here. It's potentially a second repeat invitation, right? So a lot of the prize winners actually go on and participate regularly, and part of the prize is that if you start to get engaged, we bring you back a second time, even without a talk and without an award. And that has happened actually, I think we had 26 winners up until today. Well, no, 28 now, but 26 of them, 11 came back on ISOC money and 13 came back on their own dime. So there is quite a sort of good history of pulling people in through the prize. And the sponsorship helps us bring the people back. Right, so with two talks, both of them are, or used to be students from Olivier Bonaventure, which is pretty impressive. So here's two prizes going to UC Louvain graduates, if I see that right. So congrats, I guess, to the group. And even more impressively, they're on completely different topics. One is multi-path TCP, the other one is routing. So that is also very interesting. So one is for fibbing. I think that's the one we go first. And the second one is application control for multi-path TCP. So congratulations. Before we go to the talks, is there anything that people want to bring up sort of IRTF-wise in general? Or is there any chair here that sent me email about a news update that I didn't put in because I didn't read my email in the last hour? Going once? Going twice? All right, twice is enough. All right, so Olivier, you're first. And I will make this big. Hang on, normally, isn't there any way to get this bigger? No, maybe like that. No?
No, I can't switch it.
Oh. Yeah, I did slideshow, but then there's also a way to zoom it still, right?
You did full screen.
Oh. Ah, thank you. All right. Anything else you want me to press or touch? No.
It doesn't work.
It doesn't work? Okay. Is it the right one because there were two?
That's yours.
Okay. It worked earlier, so let's try again. Are you going to the right? Okay, maybe the battery ran out. Tell me next slide.
Right. Hi, so I'm Olivier. I'm from Belgium.
Speak into the microphone.
Yeah, sorry.
Really close.
Is it better? Hi, so I'm Olivier. I'm from Belgium, from UC Louvain, supervised by yet another Olivier. And this is joint work with Stefano Visicho, Laurent Van Bever, and Jennifer Rexford, who, well, have worked at least as hard as me. You can skip. So we'll talk about fibbing. So some people yesterday told me, is this open? Yes, it is. You can switch to the next one. And so we call this fibbing because we want to lie to the routers to control their fib, literally. So that's as simple as this. I'm sorry you will have to skip a lot.
No problem.
So to start off, to understand what we mean by this, right, before I get started, if you have questions, be sure to just ask them right away. That's going to be easier to follow the rest, basically. So if we start with this simple network, so we have, well, the usual icons that are from Cisco and a bit heavy. If we switch to the next one, it's easier for us as researchers to just use graphs. So nodes for the routers with a particular name and edges. Yes, you can switch to the next one. And so for routing, when we speak about intra-domain traffic, we use link set IGPs, typically, such as RESTWave for SIS. And these protocols basically compute and try to share the network topology in order to, you can switch, in order to compute the shortest path on the graph to forward traffic in the network. So for example, here I had a prefix, so some reachability information advertised on the control plane on the left. And the protocol managed to compute the shortest path tree to forward the traffic, giving the pattern shown on the right. You can switch. So traditionally, with this set of protocols, we have what we call a descriptive management process. So that is, you have the operator, maybe you, that has to figure out what he wants to do. You can switch. And then that has to figure out how to do it. So I want to have this particular policy in my network. I want this set of paths. And now I have a bunch of routers that I need to configure. So I'll provision the configuration for each of them. We can switch. And from there, this is a distributed protocol. So we have every router that's able to independently compute the shortest path in order to forward the traffic, as we've done before. So they take some input, derive fib entries, and push them in the line card. You can switch. So in the research world, there's been actually quite a lot of interest over the past few years towards SDN, so software-defined networking. So we had OpenFlow 8 years ago, and now the new trend, the new hot topic is P4. So the way it works there is that instead of having a distributed control plane, we have a centralized one, so some software running somewhere in the networks, and then super simple devices, like switches, for example. You can switch. And so in this management model, we have what we call a declarative management model for the operators, because the operators just has to think about what he wants the networks to do. And so express requirements, you can switch, to this centralized control plane. So let's say 1 or 2 servers that need some configuration input. And this centralized controller will then do all the heavy lifting on its behalf. So in this case, compute the path that match the requirements, the fib entries that need to be set up on every single switches, and push these fib entries towards the switches. So that sounds great, but there's like a lot of errors. Well, there's one error that goes to the controller and a lot of errors that goes out. So basically, we have a bottleneck in the network. So we have this huge program that's a single part of failure. And, well, there are quite a lot of other challenges yet to be solved. We can switch. So basically, we have this state of the art in the sense that we have on the left what's been mainly used up to today, so distributed protocols. So these are super scalable. Well, the internet works today, and we have a BGP routing table that has over 600,000 prefixes. I think these numbers speak for themselves. These are fairly robust. I mean, usually you have access to the internet and it works. And on the other side, we have SDN with a lot of other promises, like it's easier to manage because there's just one centralized controller. It's more flexible because with OpenFlow, you're able, for example, to do more than just destination-based forwarding. You are not restricted anymore to plain shortest path routing because that's what the device supports. You have some gains there, but you can switch. But yeah, this comes with a price, and so the focus of this work is, well, we are looking what's in between these two. So we are trying to find a bit of a middle ground approach, you can switch, which we call fibbing, and where we aim to be as manageable and close to as flexible as pure SDN solutions, but we still want to be able to scale properly and to be robust to failures. So for example, if you take the SDN one, the easiest failure to understand is you lose the controller where nothing happens anymore. The switches are not able to recover from themselves. You use an IGP, you break a router, well, all the others are able to take over. We can switch. And so that's what we are going to cover today, which is, well, how do we get to make this fibbing, this architecture that's a bit in between these two paradigms in the network. Go ahead. So we start from the same basic idea in the sense that we want to be as manageable as SDN. So we have a centralized control plane, a controller program, a single interface for the operators, but we still want to keep the distributed aspect of the control plane for scalability and robustness concerns. You can switch. So in this particular model, we have the operator that, same as for SDN, just express some requirements to the controller. So it's easy for him. He just has to state what he wants and doesn't need to care how it's implemented. So the controller itself will figure out what are the paths that need to be set in the network in order to implement these requirements. We can skip. And then we want to play with these distributed control planes, for which we still want to be in charge of programming the FIPS, basically. So we don't want to have our controller touching each individual hardware. So how do we do this? Well, we use a well-defined API, which is the IGP message themselves. So if you think of OSPF, these are the LSAs that you have. So these are, in a way, some form of API, because when you have IGPs in the network, well, you know that each of them will only be able to run shortest path computation, but they will do so on a particular graph that they infer. This graph is built by the IGP message that they exchange between each other. So if we manage to send some message that we control, the intuition here is that we can basically modify the input of the computation in order to control the output, which is, well, the set of paths that are found in the network. We can switch. So how does it work? Well, if you go back to the sample networks we had before, so in this network, we would like the path towards the blue prefix to take a different, oh, I forgot the cost, to move around. So earlier on in the network, you had every single path from A, B going through router 2 towards C. And in this case, we'd like just the blue prefix to go all the way around, so a bit more on the left, in order to select another path for a single prefix. So that's something you're normally not able to do with normal IGPs, because both prefixes are reachable through the same routers. And, well, one of the conditions for IGPs to work is that we don't want loops, so we cannot have two disjoint paths for these prefixes. But that's what we want to do in this case. Let's assume, for example, that the blue prefix requires the traffic to go through a firewall that's only located on the link between R1 and R2. So we need to be able to do this sort of distinction. You can switch, sorry. So with this information that's been fed to the controller by the operator, it's going to figure out what is the modification that I need to do to the IGP topology in order to implement this new path. So in this case, it decides, you can switch. So in this case, it decides to send an IGP message with some information to the router closest to itself, so through the IGP adjacency. This is a link state protocol, so this single message that's been sent by the controller will get flooded throughout the whole network and eventually reach every single router in the network. So that's easy for the controller to speak to anyone. He just has to send it to its closest neighbor, and the protocol will relay the message for him. You can switch. And there's the fibbing part. So we've sent a message asking to create a fake node, so a fake router in the topology that we've called FA. And that also asks to create a fake link that links this new node, this new router, to an existing one. So if you just look at this topology with the set of weights, of link weights that are on the graph, if you do the work from the control plane, you can skip, you are able to compute some new shortest path on the graph. So if you take the shortest path towards the red prefix, well, nothing has changed. However, if you compute the shortest path towards the blue prefix, well, all of a sudden, you prefer to use for router A, the next stop, FA. So this new fake node that we've added on the IGP topology. So that's, well, that sounds great like this, but that's just a control plane. That doesn't tell you anything about where is the traffic going. This is not a real router. It's not even connected to a real physical interface, so that's not enough. Go to the next slide. So there was a third line on the IGP message, which was a physical mapping between these fake elements, this fake node, its fake link attached to the router A, and a real physical element, in this case, AR1. So with these three information, we have modified the control plane topology. So we've added a fake node with a fake link to a physical router. We have selected a cost that caused some new shortest path to be computed. And then we have some information on what's the actual physical interface I need to use to reach that fake node. So if you are able to implement these kind of features in a routing protocol, well, the hope, and actually that's the result we have, is that when you switch from the control plane view to the data plane to actually measuring the traffic flows, well, you see that all of a sudden you have different set of paths that are being used for two prefixes that share the same egress router. So in this case, we've managed to steer away the traffic towards the blue prefix over a longer path, at least compared to the original situation. So that's a short overview of what we call fibbing, which is this idea of lying to routers, in this case lying to router A, about a new neighbor that doesn't exist, that should be reachable with a particular cost, and that's announcing some destination prefixes. You can skip. There's more to it. So we've started with a single fake node that we've added on the graph in order to trigger one next stop change. We could do it more often than that. You can skip. So we've changed the requirement to, and we want now to implement a path that goes from A to R1 to R4 and then towards the blue prefix. And so in this case, we need to do two next stop changes. So we need to go on, well, to first cause A to change its next hop, to pick a longer path to reach the prefix, but we need to do, we need R1 to do exactly the same. So we can send twice similar information to add new fake nodes on the graph, new fake router on the graph with chosen cost, and cause you can skip, and cause the path to be constructed and to follow, again, this new shortest path that we have on the control plane and triggered on the data plane as well. There's even more to it. So we've added 2 fake nodes on the graph, and well, if you think of a network that has, let's say, 1,000 routers, if you want to make a very complex path, you probably don't want to send 1,000 LSA, 1,000 IGP messages to implement that particular path. So in this case, with a short path, and we can simplify it. So by selecting properly the cost that we use to announce these fake nodes and to link them to the graph, we can minimize the number of messages that we send. So this is just an intuition. The algorithms themselves are rather long, but you can go to the next one. But if we take the original graph that implements the path that we wanted, so the path going over on the left, we are able to construct what we call a reduced topology, where we inject the minimal number of fake nodes that implement the specified requirements by playing with the cost of the fake nodes that are chained together. So if you look yourself on the right, you'll see that with the chosen cost, only the routers that are supposed to change their next hop will do so, and will do it accordingly to the requirements from the operator, still leaving the path towards the birth prefix unchanged. You can go to the next one. So I've mentioned algorithms. So we have 2 classes of algorithms. We have one that's super fast, that was the one we use on the left part of the previous slide, which lets us compute augmented topologies. So these topologies on the control plane side with the new elements super quickly. So to give a rough approximation on a network with about 2,000 edges and 300 routers, we're able to compute a rather huge amount of change in a couple of milliseconds, around 2 or 3. And you are able to reduce heavily the number of fake nodes, the number of IGP messages that we want to send in a network in about a second. So by playing with these 2 algorithms all together, we are able, for example, to react quickly to failures. So if we see a failure, we are able to compute the new desired state of the network within milliseconds and optimize it over the longer run to reduce the overhead on the routers. You can see it? So we said at the start that we wanted to keep the desirable properties from the IGP, so the fact that they scale a lot to huge networks and that they are robust to failures. So we still have this. We're still using intra-domain routing protocol as the basis for a control plane, so we are still able to withstand failures. If all of a sudden our controller fails while the network is still working, it's still an IGP, the classical one that you've been using up to now. And we can do a bit more than this. So we're able to implement some form of security policies, such as fail close or fail open. So if the controller fails, do I want this particular traffic flow to still exist in the network, or should it be dropped because I can no longer enforce a security policies? So that's some benefits that we have because we are able to centrally control the forwarding state of the network. But this is still with an IGP with the scalability and robustness benefits. Go to the next one. And so expressivity-wise, for the requirements that the operator is able to specify to the controller, we can enforce any forwarding DAG, so any set of path that does not create a loop on a per destination basis. And when we say per destination basis, that's an IP prefix. So a /16, a /120, a full /128 if you're in IPv6. So we have a resolution that ranges from a single physical machine to a whole network, with any set of path without affecting the others. So we believe that's pretty useful, actually. And so we have a few use cases that we developed in the paper and in other labs and so on. And I'll present you one here. You can skip again, actually. And so in this case, we've built a demo that we presented a few months ago, where we targeted the issue with flash crowds network. So these sudden surges of traffic. So for example, one of your friends of Facebook saw a new video that he really liked, shared it to all of his friends, who did the same, and all of a sudden you have 10,000 users that all want to use the exact same video coming from the same geographical area, and so hitting roughly the same CDN. And that only lasts for a couple of minutes, because when they've seen the video, they are no longer interested in it. And so it's actually super hard to protect against it. However, you still want the people to be able to see that particular video. So what are the solutions? If you skip to the next one, well, currently, operators have basically no choices. They have to over-provision. So it's super hard to protect against an event on the network that lasts for a couple of minutes and probably never happens again. So yeah, you buy bigger pipes, and that's all you can do, realistically. So we wanted to look a bit at how the ability to program an IGP could help to solve this issue. Because the main reason why you cannot really do something more clever than just over-provisioning here is that if you want to change the forwarding state of the IGP, as of now, well, you have to reconfigure all devices independently. But now we have the ability to do it centrally. So if you go to the next one. And so we built some experiments, well, in a controlled environment. And so we had a few video servers, a couple of dozen of clients that all of a sudden wanted to try to get access to a video, to stream this video, and we were monitoring the link loads in the network. And the goal was there to ensure that every single client was able to actually view the video without stuttering. And so we actually built the topology that we had seen before with the same set of link costs. And in that particular topology, if you put the video servers on the if you attach these to the two routers A and B that I've drawn on the right, if all of a sudden you have a lot of clients hidden behind the same prefix, so in the same residential area, that all start to want to access videos coming from that part of the network, well, in this case, you have a bottleneck. You have a single path that's available from A and B towards C. These are the same, while you just sum up the load over the links. If you get a number of people that's large enough, well, you have a huge link utilization imbalance in the networks, or congestion, depending on how big it is. You can skip. So fibbing lets us program paths in the network. Well, there's an easy fix here. So we see that all of a sudden we have an increased load over the same central path. Well, why can't we just spread the load? So LinkSet IGP supports CCMP, well, by default, natively. So in this case, the goal is, well, I want to use multiple paths, for example, starting at router B towards router C. Well, let's add a new path in the control plane, which has the same cost than the old one. So if you look at the fake router that's been attached to the router B, it's advertised with a cost of 2, which is the same cost than the old path you had, which was B R2C. So now router B, at least on the control plane, is able to compute two different shortest paths towards the same prefix. And so it's going to try to use both of them, eventually resulting in the load spread that we have on the right. We can do more than that. If you go to the next one, we can do the same behavior on router A. So if we introduce a path, a fake node at router 1 with a chosen cost that's reachable from router A, and I got the cost wrong, whatever, we should be able to spread the load fairly easily between the two paths that are available. If we do that, we're able to spread the load evenly across two paths. You can go to the next one. And we can do even more than that. By adding more and more information on the control plane, we are able, for example, here to cause to introduce uneven load balancing on router A. So if I had two different fake nodes on router 1, I see two different IP next stop for router A. And eventually what I have is that I have a splitting ratio on router A that's 1/3 and 2/3, resulting in, well, a much lower overall link utilization in the network. If you go to the next one. So we built this experiment and recorded measurements, obviously. So we had initially a single client behind router C trying to access videos on the first server. And over time, we gradually added more and more clients that were trying to request video from either of the two servers, eventually congesting the bottleneck links, so B or to C. And so we plugged our controller in, fed him with the link load measurements that we had. And so over time, we started to add these new equal cost paths. So the path that goes from B towards R3 to spread the load once. That's the first reduction, the first drop in bandwidth consumption that you have on the graph. So at roughly 31 streams. And then again, when we started to add more and more demands from the clients behind router C towards the second streaming servers, well, we added another path starting at router A to decrease again the overall link load. So if we do this, well, we basically were able to increase the available bandwidth towards router C, starting at router A and B. So avoiding congestion in this case. And we've been to react like this in milliseconds. If we start over from the idea of flash crowds in the network, well, once the event is done, once people no longer want to access the content, well, we can just remove these extra fake elements that we had added previously in the control plane. And so stop using these new paths. So we're able to change the state of the network quite fast and just to fix temporarily whatever's happening based on the policy that we have from the operators. If you go to the next one. So I've said that we made an experiment for that. So implicitly, this means that we're able to get a working prototype. So we have running code, we have something that does this idea of lying to routers in order to change the next stop selection. And so this works using OSPF. So we're leveraging some features found in that particular IGP. Because that's a link state IGP, it's actually super easy for us to bootstrap the controller. So we plug it into a physical router and we receive the whole topology directly from the LSAs. So that's fairly easier than with SDN, where you have to reinvent everything from MLDP to whatever this topology discovery protocol you have. And we've confirmed that this works against Cisco iOS, NXOS, and JunoOS, well, the hardware that we had. So this works, again, current router, unmodified. Well, we're able at least to solve the use case that was done before. You can go to the next one. So we use specific types of OSPF messages. So you have a wide range of link state advertisement messages that are available in OSPF. And more importantly, we have these two subtypes, the type 5 and 7, which enable a router to announce the reachability towards a specific IP prefix, but also mention a given IP next stop in the network and associate it to a particular cost. So using this set of message, I can position a fake route advertisement wherever I want in the network and select the cost. So if I want to do this, I'm actually approximating the model that we had before and able to modify the path that are chosen by the router in the network. There's, however, one single drawback from this, which is the fact that we don't want yet to modify the protocol, which is that we've seen on the previous slides that sometimes we want to chain these fake nodes. So we want to trigger multiple next stop changes for the same destination prefixes. So there's one catch with type 5 LSAs, which is that if you want to send multiple LSAs announcing reachability for the same prefix and don't want these to collide, you basically have to provision several OSPF router IDs. And so when you think about the controller that we have in the network, it's actually multiplexing a lot of virtual routers to generate all the needed router IDs in order to chain all of these. That's one of the limitations we currently have with the solution. We'll see what people could get for a cleaner solution. If you go to the next one. We've run extensive benchmark, also helped by the Cisco lab in Brussels. And so we've tested this with 100,000 LSAs that were fed to the routers in order to cause forwarding changes. And basically, there was no impact on the shortest path computation. So this whole process of sending IGP, sending control plane message to change path, etc., is basically for free, at least on the controller side, because, well, that's one of the quirks of the OSPF implementation. That's a vector addition. It hits basically no RAM on the routers. So 10,000 LSA hits about 10 megabytes of RAM. So that's close to nothing. And triggering one next up change is almost a constant time, at least on the routers we've measured. And we're able to send, to cause 100,000 next stop changes in the fib in about 90 seconds. So that's close to the 900 microseconds per single next stop change that we want to set up. So it's actually super fast to do this. We're able to send network-wide updates on the path to be chosen within milliseconds and actually have them be implemented. I've started to mention some of the drawbacks. So we're using unmodified OSPF. Well, we first of all are limited by what OSPF offers. So we are not yet close to this whole idea of adding a fake node and then a destination. We kind of have to group them together and plug them on the router. So if you we look into the algorithms, well, there are differences in the expressivity models, and it's actually a bit harder to do whatever we want with pure OSPF than what we wanted in practice. There's one huge limitation, which is that OSPF ranks link state advertisement depending on their type, and will ignore type 5 or 7 LSAs if it has received another route toward the same prefix of a preferred time. So literally, for example, an intra-domain route. So to get this to work, well, we had to do some bit of engineering just to show that it's feasible in practice, but obviously we'd like to get something cleaner in the end. And I've spoken a lot about OSPF. Well, that's because it doesn't work yet with SIS. So we don't have this ability to send a message that gives us reachability towards an IP prefix, given an IP next up, and some metric. So there's no way to do this with ISS as of now. If someone has an idea on how to develop some clean slate extension, we would be more than happy to look at that, because that's, well, we believe there's value to expand this and make something cleaner. Skip to the one. And so just to conclude, so we've started to look at what we could do with this ability to program path in an IGP. And the more we looked at it, the more we're able to do. So for example, we've seen that we're able to modify path and cost almost independently on a per prefix basis. Well, there are a lot of protocols that rely on the path and the cost that are chosen by the IGP. So for example, the BGP decision process has some criterion that depends on the cost of the route. So by doing, again, some fiddling there, we are able to control the output of the BGP decision process. So in order to control a bit, what would be the path chosen by the transit traffic in my network, and make these vary over time. We believe that having the ability to do this kind of exception routing can simplify the configuration process on the routers, because you could get simpler configuration with a lot of ECMP new networks, for example, and program the very specific path that you need for the few prefixes that require special treatments. Maybe the data centers, the entire data centers traffic that require a separate path. And finally, this ability to program the network within milliseconds opens, at least for us, a new domain where we're able to do real-time traffic engineering. And so there's a paper at the upcoming Connect, so that's in about a month, that implements optimal traffic splitting in the network at all times, so that ensure that you are always able to maximize the link utilization in your network, which is fairly interesting and which leverage fibbing actually. The closing remarks we have is that we've built this whole system centered around the fact that, well, we have these routers sitting in your desk. What can we do with these? We have this formalism of adding fake nodes, fake links, and playing with the weights, etc. Is there a better solution? Well, if you have one, we would welcome it quite a lot. And we would, well, I would be happy to take questions on any part of this.
Thank you. Questions? And say your name for the minutes, please.
Philip Matthews. So I have two comments. First of all, your approach looks actually rather similar to segment routing. Have you, I don't know if you've looked at that or not, but it has similar problems and similar solutions to that. So just a suggestion to investigate that. The second comment is that this approach works well for certain types of ISPs, what I sort of call the classic ISPs, which run, take internet traffic and run it as IP traffic in the core. But there's the sort of the newer class of ISPs that don't do that anymore. They put them inside L3 VPNs instead, okay? And this approach doesn't work for L3 VPNs. So, or at least not directly. Now, the question is then, can you modify it so it actually would work with an L3 VPN?
So there's two points. So the first one was segment routing.
Yes.
So we're actually playing with segment routing on the side quite a lot. More specifically the IPv6 data plane, because that's the one we are able to implement in the Linux kernel. So we believe there's different use case for both. So segment routing requires you to attach a header, a stack of labels to every single packet. Well, if you have long-lived flow, you might just not want to do it for a reason or another. Doing an even load balancing with segment routing, at least for the solution we've had, I've been told yesterday that there's an IRTF for that, but in our solution required to do some stateful load balancing, which was not very scalable on the hand host. And we are able to have this idea of triggering multiple next-up changes network-wide with a single message. Whereas for segment routing, you have to reach out to every single ingress. So that's a separate part, but yeah, segment routing is something we look into it because it does quite a lot of interesting stuff as well. For the L3 VPN stuff, that's the comment on the very last slide, which is, I believe L3 VPN is dependent on LDP for the MPLS label propagation, so that you are able to route through the core. Well, LDP depends on the IGP to select its path.
Well, that's if you use LDP for it. If you don't, if you use RSVP, then obviously that's a different way. And operators do one or the other. So.
Yeah, so there's that as well.
But still, you want to, it's different because you still would want your, you still want to influence how things go between L3 VPN instances there, which may be different than what you want, traffic, other types of traffic like management traffic, which is typically, sent as straight IP traffic around. So I don't think, and in that case, you probably also, if you do that to affect one, then you would end up affecting, if you have multiple L3 VPNs, you presumably just want to change one. They don't want to change all of them. So I would say you would want to instead play with BGP rather than play with your underlying IGP.
Which is something we also do. So since we control the cost, we can change the cost that BGP sees between the different egresses. And so by, again, doing some crafty engineering, we can cause BGP to prefer one egress over another and route the traffic towards that egress differently and cause the traffic to follow it, basically.
So you're talking about, again, it sounds like you're talking about changing the IGP cost to affect how BGP changes. But I'm saying, at least from my point of view, I don't think that would be the way an operator would want to do it. No. Instead, they'd like to affect the actual L3 VPN routes themselves for a particular L3 VPN.
Well, I'm sure we can dig this offline. It would be maybe easier for me just to draw what I think and maybe understand what you're saying then.
Okay.
Questions? Where are all the routing people? Yeah, everybody looks at me, but nobody gets up. No. Allison is coming.
So you mentioned that in the paper that security can be handled by doing MD5 authentication in the OSPF context, but by introducing this fake node, are you also allowing the possibility that other fake nodes could be introduced and they could, provide routing information you didn't intend, and you might need an object-oriented security rather than a peer-type security?
So, so the MD5 mention that we made in the paper is a statement that, maybe it was poorly phrased, but we have the controller that's seen by all the routers in the network just as one of them. It establishes a normal an IGP adjacency. So we share the MD5 key between the controller and all the routers, and from then on, it's seen as the same OSPF area, to put it that way. And so the message we sent are authenticated because that's the operator himself that set up the controller. There's no possibility for someone else to send an LSA that would not be authenticated.
Okay, I guess if you were going to operate that, it'd be good to have a detailed explanation of how not to introduce a risky situation to the network. But thank you. Thanks for that comment. This is.
You broke it.
Sorry.
All right. Did you guys not get enough coffee in the break? It seems like it. Okay, thank you very much. Second talk. And can you try your dongle for the next talk, since this one, I guess, ran out of battery? Slideshow. Pause. Let's see if this works better. Want to check? I guess it's my Mac. All right, I'll do the next slide thing and. Oh, okay, keeps me awake. All right, second talk is Benjamin Hesmans, also from our US group at UCL, who's also doing quite a bit of MPTCP stuff there.
Yep, thank you. So, I don't know if
Eat
you
the
can
microphone.
because
Go very close and point it at your mouth.
It's a bit tall for me. Okay, like this? All right. So this is a joint work with Grégory Dotal, Sébastien Barré,
Closer.
oops, like this,
Yes.
Raphaël Baudouin, and Olivier Bonaventure. So, and myself, Benjamin Hesmans from UCL Louvain. So let's go to the first slide. So we are going to see first the really simple scenario in which we have a smartphone on the left side and a server on the right side, and you want to establish a connection between your smartphone and the server. So if you are using plain TCP, what will happen is that you will have to establish one pass. Next slide, please. And you will have to choose between the Wi-Fi, or next slide, you will use the LTE, but you will not be able to use the two together. So with MPTCP, what you will be able to do is, on the next slide, you will be able to use the two. So basically, it adds a layer between the socket and the TCP interface. So MPTCP lies in there. And next slide. And what is exactly multipass TCP? This is regular TCP extensions that allow packets belonging to one connection to be sent over multiple paths. So this is described inside the RFC 6824. The next slide, please. And the idea is that we do not change the socket interface. So for the applications, this is exactly the same, and you don't have to do any modification inside the application. It will immediately use MPTCP by default. And this is completely hidden to the application. So next slide, please. This one of the objective design in MPTCP. We want to support unmodified application. So let's go to the next slide. But there are various use cases in reality. So first, you may have different clients. So on the first slide, we saw that it could be a smartphone, but it could be also a router. Or next slide, again, a smartphone, or it could be also a laptop on the next slide. But that's not the only thing that could happen. Some other stuff may also be different. So if you go to the next slide, sorry about this, you will have to switch a lot. So the server side could also be quite different. So in the simple scenario, you have only one server, but you could be in a case where you have a load balancer. So this may also be a problem for MPTCP. On the next slide, you can see that you could also have multiple type of interface. So for instance, you can have a Wi-Fi interface, which is really different from a satellite link. So for instance, you will have really different RTT. Maybe the bandwidth will be really different. And so trying to aggregate them all together can be also a bit hard. And on the next slide, we can also see that the network cannot be considered to be a dump pipe anymore. So we have a lot of middle box that can, for instance, play with all the TCP options, and in this case, the MPTCP options. And on the next slide, we can also see that there are many applications, for instance, that could have really different needs, and they may want to use MPTCP differently depending on their needs. And on the next slide, we can also see that even if you have all of that, you may also have some interface that have cost constraints. You may also have security constraints and so on. So if you go to the next slide, you will see the big picture. You have all of this that could be different use cases for MPTCP. And the conclusion of this is, on the next slide, we probably need to adapt MPTCP based on the context. So if you have really different contexts, probably we should try to tune MPTCP to adapt to the different needs. So let's go to the next slide. We will first now introduce a bit more the MPTCP for everyone, just to have a basic idea of how it works. And especially, we will talk about the implementation inside the Linux kernel. So on the next slide, we can see that MPTCP itself inside the Linux kernel is already divided in small modules. And for instance, we have two specific modules, which are the path manager and the scheduler. So those are two specific modules that we can change inside the kernel to adapt the behavior of MPTCP based on the needs. So on the next slide, we will start to explain what are the responsibilities of the path manager. So first, the path manager will establish what is called the master subflow. So the master subflow is the first subflow established for the MPTCP connection. This one is a bit specific because you negotiate the option during the first subflow. And in those options, you will also exchange some material to be able to reuse after to join the connection with different source and destination IPs. So you can see here that you exchange the key, and both the client and the server keeps the key. So on the next slide, we can also see that the path manager is responsible to establish additional subflow. So to establish an additional subflow, you have another MPTCP option which is called join. You will reuse the key that you exchange on the master subflow to join the MPTCP connection. Okay, and on the next slide, you can also see that you are able to play with what is called backup subflow. So backup is not really defined inside the IRC, just tell backup, and then the implementation needs to know what to do with those kind of subflow. So this is also a decision of the path manager. And on the next slide, we can also see that the path manager will receive some events from the connection. So for instance, what can happen inside the multipath TCP connection, one of the subflow may be destroyed for some reason. So for instance, one middle box could send a reset or anything like this. And the path manager will receive an event and he will react upon these events. So other stuff may still happen. But here we'll talk about the second component that is modular inside the MPTCP implementation, and this one is called the scheduler. So in this one, when you have a queue of packets to send over a multipath TCP connection, you first have to decide which packet will be sent next. So it's not clear that you want to send the head of the queue first, because if the two subflows have really different characteristics, it may be interesting to send them out of order such that they will arrive in order at the receiver. So first you pick the packet that you want to send, and in the second time, on the next slide, we decide on which subflow we want to send this packet. Once we have decided, we send the packet over the subflow on the next slide, and we add a specific multipass TCP option that will map the TCP sequence number to the MPTCP sequence number. So we have two levels of sequence number, and inside the MPTCP DSS option, we have the mapping between the TCP sequence number and the MPTCP sequence number. So we can go to the next slide. So here you have just a small summary of everything that is modular. I'll already explain all the details, so we can switch to the next slide. And this is a great thing. We know that MPTCP is modular, so you can switch some part of it inside the kernel. But the problem is that it's still inside the kernel, and it's still really hard to develop a new module inside the kernel. So we want to bring all the modularity from the kernel and push it up to the user space. So the idea really of this work is try to move the pass manager from the kernel side to the user space. So the result of it should be that it should be more easy and more flexible for the user to develop new pass manager, and it should ease the development. So let's go to the next slide. And now we will briefly describe the solution at a really high level, just to have an idea of how it's implemented. We have one part that is implemented inside the kernel space, and the other part is implemented inside the user space. So let's go for the kernel space. We have a module that replaces the pass manager on top of the already existing interface inside the kernel. And instead of taking any decisions, so let's go to the next slide. What we do instead of taking any decision, if we have an event from the MPTCP kernel, we translate this event into a message, and we will put this message onto a netlink. So netlink is a protocol that will let you send message from the kernel to user space. So we just pack the information inside the message, and we will send the information into user space through netlink. So this is an example of event that we could have. So for instance, the MPTCP kernel could say, hey, I've got a subflow that is destroyed, and the module, instead of taking any decision, would just pack the information inside the message and send it to user space. So on the other side, what we can also do is listening to the message that comes from the user space. So the module itself will listen from user space, and you can receive new messages that it will translate into MPTCP actions. So the example for this one on the next slide is create a new subflow. So the user space will tell, hey, I need a new subflow. It will pack the message, send it to the module, and the module will translate the message into MPTCP action such that a new subflow will be created. So after that, we have on the next slide the user space implementation. So in user space, we just add a library that is able to listen to the applications themselves. And the application can send a message to the library, and the library will translate the message to netlink. So let's go for the example. So again, just the library is just listening and will translate it all the way down to MPTCP. On the other way, to the next slide, we have also the same thing on the reverse pass, and the library itself allows an application to register callbacks so that if an event happens, it will call the application to tell the application, hey, I've got a new event. So again, I think we have a small example on the next slide. So this is the same as previously. So the subflow is destroyed. It goes through the module, then to the library, and the library itself calls back the application to tell the application that we have a subflow that is destroyed. All right, so let's go to the next slide. So now we have the basic solution that has been described. We will go through two simple use cases. So if you have any question I forgot to tell you, please ask now. Because I didn't go into details for the implementation, but if you have any question about the implementation, please ask right away. So for the use case, we have two of them. We will start with the first one. So let's go for the first one. You are in a simple scenario where you have a smartphone and you have a Wi-Fi access and an LTE access, and you want to connect to your server. So in today's implementation, you will use the default path manager, which is called the full mesh. This path manager will open a subflow over the default interface on the next slide. And then immediately after, it will also open another subflow on the backup interface, even though it does not plan to use it. So it will still open this subflow. So now if the smartphone user is moving away from the access point on the, yes, sorry, I forgot that. Yep. So if the smartphone user is moving away from the access point, what could happen is the subflow could become really, really slow. And if the subflow is still there, MPTCP will still consider it as active and it will not send any data on the backup interface. One of the things that is important here is that slow is somehow subjective and we don't know really when to consider a subflow as slow. So this may depend on the application, for instance. So if you are using a small application that does not exchange many data, slow can be enough, for instance. But if you are looking at a YouTube video, for instance, maybe just a few kilobytes will not be enough and you will need to use the backup interface. So we'll go to the next one. So I already explained that. So the two issues here are the subflow is established really too early. We establish it whenever we don't need it. And when we need it, we do not use it because we never define exactly what is a slow subflow. So let's go to the next slide. So now we have implemented something different. We propose something different and we implemented inside user space. And what we propose is to use the same default interface, establish the subflow just as before, but now in this case, we are not using the backup interface. We will not establish any subflow on this one. So let's go to the next. And then we still have the same issue. The smartphone is still moving away from the Wi-Fi access, but now we detect that the subflow is considered as slow. So what we will do now is open a new subflow on the backup interface, and we do not describe it as a backup, and we will start to use it immediately. So now we have those two differences. So the difference is we do not establish the backup interface immediately, and then when we detect the slow subflow, we open a new subflow and we use it immediately. So let's go to a small experiment. So that is the same but described in text. So we can go to the next slide. So we have still the same experiment. Let's go to the next slide. And we will just exchange a small file from the smartphone to the server. And let's go to the next slide. And after 1 second, we will emulate the move away from the Wi-Fi access with a 30% losses on the default interface. And then we will compare the two solutions. So the today's solution, which is the default path manager inside the kernel, which is called full mesh, and our solution that we called here backup redefinition. So if you look at the sequence number evolution of the today's path manager, what will happen? So here we have a graphic with the sequence number on the y-axis and the time on the x-axis. And what you can observe here is the sequence number at the MPTCP level. So in green, you have the master subflow, and in red, you have the backup subflow. So here, you can see that we are not using at all the backup interface, even if it's there. And the green subflow is still in use, even though it's really slow and we do not manage to terminate the connection. So let's go to the next slide. So here we see all the TCP retransmissions. So at this point, we know that there is a problem, but we do not do anything. And the time to exchange the file is really, really long. So let's go to the next slide. And I already say that the backup subflow is not used. But if we use our newer definition of backup, what will happen is at start, it's exactly the same. We open the master subflow, we exchange a lot of data. And then after 1 second, we have losses. If we go to the next slide, we will see them. We have losses, and the RTO is growing. and then MPTCP is, well, the user space path manager detects that the RTO is growing, and we will open a new subflow, and then we will use immediately this new subflow, and we will be able to terminate the connection, in this case, in 4 seconds. Yeah. So in this case, we complete the exchange of the file, and on the previous case, we did not complete. So if you look at the left side, we should go up to 10 if we want to terminate the exchange of the file. In the default case, in the current implementation, it's not even possible to terminate the connection because MPTCP will still try to exchange new data over this subflow, even if it's not working well. On the other side, in the user space path manager, because we detect the RTO, we are able to open a new subflow and use it immediately. So that's the end of the first use case that we wanted to present. And the benefit in this case is you can probably save some energy on the smartphone because you don't need to open a new subflow immediately. You will probably save money because you still have to, in the first case, you still have to exchange the SYN. In this case, in some of the cases, you will not even exchange the SYN. And then you will have a faster recovery. So on the next slide, we'll go to the second use case. So this one is totally different. Let's go to the first slide. So this is a completely different use case for MPTCP. MPTCP could be used, for instance, in data centers. Even if the clients and the server have only one interface, it's still possible to use MPTCP. So in this simple topology, we have ECMP on the next slide. And what he will do, he will use the IP port source and destination, and he will hash them to decide on which path he will send the subflow. So for instance, the idea behind this one, you can open a first subflow and it will go on the first pass, and then you will open a second subflow, it will go on the second pass, and then a third one and a fourth one. And the idea is that you will aggregate all the bandwidth of all the paths with that. So we want to know if it works or not, so let's try a small experiment again. And we use the same topology, and we exchange a file over this topology, and we measure the completion time. So maybe go to the next one, yes. So we just use 5 as a parameter for NDIF ports, so it means that we will open 5 subflow on this particular topology. So here is the result of the completion time of all the experiment, and we can see that there are three clear cases. So what happened in this case? Well, we'll see it on the next slide. So there is nothing to prevent all the subflow to go to the same path actually, because you don't know what is the hash function exactly. So what may happen is that all subflow may end on the same path. And at this point, they will not aggregate bandwidth, they will share the same path. So if all subflow use the same path, you will not gain anything. So let's go back to the result. Here, actually, what we did is that we found we found 2 out of the 4 paths. Then we found only 3 on the next slide. We found 3 of the 4 paths, and then actually we found all of the paths on the last one. Okay, so can we do something better by implementing a new path manager in user space? Yes, we can try to do something. So the idea is trying to detect when 2 subflows share the same path. So in this case, we want to be able to move the orange path onto the second link. So how do we do that? We have a proposition. So instead of just opening n new subflow, what we do is we start by opening the same number of subflow, but then every t seconds, which must be defined, we will we will just take a look at the pacing rate of all the subflow, and then take the subflow with the lowest pacing rate, closing this subflow, and then open a new subflow. And the hope is that we will find the subflow that is on all the subflow that are on the same path, and then try to find all the paths. So let's go to the next one. So we retake the same experiment, and we compare the 2 solutions on the next slide. And what we can see here is that with our solution, we push the completion time to the left, and we are always more or less finding all the paths. But it comes at a cost on the next slide, because we are reestablishing new subflow really frequently. We are often in the slow start phase of the TCP. So we are losing a bit of time on the best possible time, but overall we are still pushing the completion time to the left. So we can go to the next one. So that's it for the use cases. And now we'll just take a few minutes to describe the socket implementation. So on the left side, you have the solution that has been presented inside the paper. So you have the specific module, the library, and a lot of stuff. So this one is quite huge and is quite flexible. And on the right side, you have the socket option solution. So this one is much, much easier. And actually, what we did is extending the socket interface inside the Linux kernel. So you have systems of socket that is already defined, and you have get and set socket for this socket. And we extend those to be able to control MPTCP directly from the application. So now you no longer have all this auxiliary stuff. You have control immediately from the application to the kernel. So here is just a small example. So this was attended for the hackathon. So we did it during the hackathon this weekend. We use the API and we produce some result. If you are interested, we have a list of results that we had this weekend. So from a C code, you are just able to create a new structure and put the address over there and just create a new subflow with a regular get socket. So let's go to the next. Here is just a simple list of the things that you could do now in user space through the socket API. So basically, you are able to get a list of all the subflow. You are able to know which subflow use which address and port. And you are also able to open and close subflow inside the user space. Yeah, let's go to the next one. So in conclusion, what we add here is a new flexible API proposal for MPTCP path management, and we have some use cases to prove that it's possible to do. And we think it might be useful in the future to be able to have more deployment for MPTCP. So now the deployment is quite small, even if it started, it's still quite small. And we think that with this kind of API, we could have a larger deployment. So if you want to test it, it's possible. MPTCP is always available at multipassTCP.org. And the socket API is also available on the mailing list on the site. And we have also a virtual machine that is available on multipassTCP.org. So you can just try it. And we can go to the next one. I think that's it. If you have any question, I would be happy to answer them.
Questions? Wow, we're never going to do this on Monday again.
Do you plan to extend the API to be more high level, available, for example, for browsers or something?
Yes. So when we designed the API, we had a lot of questions, such as what should be the right abstraction. And we find out that it's very hard to get an idea of what the application will want. So instead of having a high-level API, we started with something simpler, with the idea that we could build something more complex and more abstract with this simple API. So we will do it, yes, for sure.
So it seems like the application will need to gain a whole lot of knowledge about the different scenarios it can be in order to do this effectively, right? I mean, the data center is maybe a special case because there you have a pretty rigid topology,
yeah.
but an application that runs on an end system that's, we carry around could find itself in very, very different environments, and so it would need to implement quite a bit of smarts.
So one of the use cases that we did not present it was the streaming use case. So for instance, if you know that you need a minimal bandwidth, you can stick to one subflow as long as you have the minimal bandwidth to exchange the file to get the video streaming. And if you know that you will be too slow, you start, for instance, to open a new subflow inside the application to get fast enough so that the video is not stopping, for instance. So that's something that is more for the application itself.
I'll keep going if nobody else goes. So you, in your examples, right, it was always the client that was doing stuff.
Yeah.
But you have an MPTCP stack on the server, which also has this API,
Yeah.
and which can also try to express its wishes.
Yeah.
And what if the two don't align?
What if the?
What if the two logics on the client and the server try to do different things to the connection
Yeah.
through the API on each side?
Yeah, that's also something that we discuss. It seems that at some point we will have to have a mechanism to exchange the high-level requirement between the server and the client, probably. So we could also start to insert new mechanism to let the server and the client talk outside of the data or over the TCP option, for instance, to know what are their objectives.
It might not always help, right? So for example, if you have if the server would prefer to use like, a path that goes through a peering link, for example, right? Well, the client would prefer to use one that gives better performance, but is not a peering link to the provider. Who wins, right? Or,
We will have conflict, yes.
right.
For sure.
Do we have an idea of how would that play out? I mean, would it just be a ping pong thing, or?
No, I think we should be able to define how to resolve the conflict before it's ping pong, as you said, but I'm not sure how to resolve the conflict.
All right, any questions from you guys? Okay, in which case we are all very early at whatever break comes next. Thank you very much and see you in Chicago.